are we okay?
Oh yeah, it just stopped.
Okay, hopefully the battery's all right still.
Yeah,
Great.
it was just a half hour, so I
okay.
turned it back
Okay,
on.
great. Sounds good.
We're back.
Okay, so this is a theoretical exercise. Two diagonalizable matrices whose sum is not. So 2 by 2 matrices would be a great size to work with, okay? So, and they want an example. That means they want you to write down the matrices you want to use. Any suggestions on what kind of 2 by 2 matrices might be best to work with? Maybe we should back up. Can anybody remind me what diagonalizable means? Deshaun?
All of the eigenvalues pull their weight.
All of the eigenvalues pull their weight, right? So if something is not going to be diagonalizable, then there has to be an eigenvalue that does not pull its weight. So that needs to be for A plus B. Well, in order for A plus B to have eigenvalues that don't pull their weight, and it's only a 2 by 2 matrix, you would have to have the same lambda twice, right? For A plus B. Do we have ways, so I guess going back to my questions about what would be good matrices to use here, do we have ways of making matrices where we know what our lambdas will be without having to like calculate that whole characteristic equation?
Like with zeros.
Say it again? Triangular matrices where you do have a 0 below the main diagonal. That's a great idea. So, because if you put a 0 here, so in other words, use an upper triangular matrix for this kind of an example. Because the lambdas now are just these two numbers. So, making sense? Okay, so Simon, what are your 3 favorite numbers here?
Like any?
Yeah, you can't go wrong. Just
5.
make them nice. 5 here, okay.
1.
1 and what?
2.
2. Love it. Great. Everybody agree that's diagonalizable? How do I know that already? I have 2 different lambdas, right? The lambdas are 5 and 2. They don't repeat. So we're in great shape on that. Okay, perfect. So A is diagonalizable. Lambda equals 5. Lambda equals 2. No repeats. That's all you need to know. If there's no repeats, then you are guaranteed that the matrix is diagonalizable. Now, if there are repeats, does that mean that the matrix is not diagonalizable? Not necessarily. We have to find the null spaces and calculate how many free variables we get to see if it pulls its weight, right? Okay. So I need another matrix, B, which is also supposed to be diagonalizable. So I'm going to use a 0 here. And now where I get to, now we can't be quite so liberal. We have to, based on what Simon's favorite numbers are, does anybody have some favorite numbers of their own that they want to use here? 2, 3, 5. Okay, now this matrix by itself also has lambda equals 2 and lambda equals 5, right, with no repeats. And I think I know where Freddie is going with that, because when you add these together now, what do we get? 7, 4, 0, and 7. You want to set it up so that you end up with the same lambda twice on the sum of the matrices. So we have a repeat now, and we now have to see whether that eigenvalue pulls its weight. So remember how you do that. You take the null space of the matrix that you get by subtracting lambda from the main diagonal. Well, if I subtract 7 from the main diagonal, that's what I get, right? Pretty much row echelon form, right? We have a pivot here. So how many free variables do we have? Only 1. But the weight of the eigenvalue, I really should have written this twice. The weight of the eigenvalue is 2. So it doesn't pull its weight, right? So the dimension, we could just write it this way if we want to be formal about it. The dimension of E sub lambda is only 1, which is less than 2, right? Which is the weight of the lambda. So it is not diagonalizable. Okay, very good. You You guys did that very, very nicely. Turns out the same thing is true for multiplication. A times b doesn't have to be diagonalizable either. Okay? So, why do I like questions like that? Well, it's because it really forces you to think about, well, what does diagonalizable mean? Or just simple matrices, and can you create situations where the lambdas are easy to work with? And upper triangular matrices are the way to go, definitely. Okay, everybody good so far? Okay, I have another theoretical problem, part B here. Consider x prime equals the matrix 2, -1, 2, 4 times x. And the question is, as t goes to infinity, what happens to x1 of t and x2 of t? As time goes to infinity, what happens to the two functions x1 and x2? No vector on this this one here. These are scalar functions. These are scalar functions. Any ideas how we're going to approach this one? Or what this has to do with?
Can we go backwards and like multiply the matrix times the vector x1, x2, and then look at it that way?
Yeah, so just so everybody understands, the x vector is just x1 and x2. So we have x1 prime, x2 prime, and then we have the matrix here, and then it's times x1 and x2. So that's where you see the x1 and x2 coming from, is there. Yeah, Deshaun?
I just had a thought. So, because the end result to like get our answer for what x1 and x2 are, we have to find our lambdas, and it'll be e to the lambda t.
Right.
So if our lambdas are negative, then that says that as t approaches infinity, it's going to be infinitely small, and as t approaches infinity for lambda is positive.
Right. Right, so what is this topic really about?
I know.
Yes, but like more, we've talked about this very recently, right? Really what I'm asking here in disguise is sort of, is the origin a source, a sink, a saddle, or a stable or unstable spiral, or a circle? Notice I didn't ask you anything about that on the midterm this week. It's just because I didn't have time, didn't have enough questions for it. But I still think it's important, and we have looked at it. So this is worth reviewing one more time. So to answer a question like this, Deshaun is absolutely right. The only thing you have to figure out are what are the lambdas. We don't have to go through the whole process of finding the solution here. We just have to find the lambdas. So that's pretty easy to get because it's just a 2 by 2. So I'm just going to take the determinant of 2 minus lambda, -1, 2, and 4 minus lambda. Okay, and so that's going to give me 2 minus lambda times 4 minus lambda, and then plus 2. And for that, this is just a quadratic again, right? So lambda squared minus 6 lambda plus 10, I believe, is what I'm coming up with. Okay, that does not factor nicely, but I can certainly just use the quadratic formula now to work out the lambdas. So -6 becomes +6 times plus or minus the square root of 36 minus 40 all over 2. Those are my lambdas. And what you'll notice is that 6 over 2, of course, is 3. And this is actually imaginary. Square root of -4, which would be 2i, which then gets divided by 2. So we just get 3 plus or minus I. Based on those lambdas, which of the 6 options, do you remember between sources, saddle, sinks, spirals, circles, what do we have here? Unstable spiral because of the +3. So basically in your solution, you're gonna have e to the 3t times stuff, right? And as t gets big, so what happens to x1 and x2 of t? The correct answer is that they blow up to infinity, basically. Because this is an unstable spiral, right? The picture would be, you know, one of these things. You can always draw a picture. I'm not looking for like super accurate pictures of these things, just a rough sketch of what the actual trajectories would look like is fine. So this is kind of what it might look like. So far so good?
The only part that makes it unstable is the 3.
Yeah, it's really just this part that you have to, the fact that this is +3. If it was a negative number, then it would be a stable spiral because you'd have an e to the negative time. So as time goes forward, it would suck towards the center as it spirals around. And if there is no a at all, it's just a purely imaginary root, then you have a circle. Because there is no exponential, you're just going in a circle with the sines and cosines here. I wasn't planning tonight to do an example necessarily of actually the Floy of those. Remember those? Just a week ago we studied this with the complex numbers. You guys just took a test. You know where your strengths and weaknesses are. If you did not do well on the problem on the midterm that had the complex numbers on it, that means you need to go back and review that again. So the fact that I'm not going to do an example tonight doesn't mean it's not important. It just means it's so fresh in our minds, and we have enough other things that I wasn't going to go over that. But you need to know whether you need to practice this complex numbers situation, and also the defective matrix thing with the W1, W2, W3. I mean, it was really interesting on the exam. I mean, there were a lot of people that got sort of both of those completely right, and you know, I know that they're on top of it. But then there were also a number of people that got one of the two parts right. It wasn't always the same part. Some people got the complex 3x3 matrix problem really, really well and didn't seem to be on top of the defective stuff. And then vice versa for other people. So you know where you are on that spectrum of the 7.4 and 7.5 material. We did the 7.6 example tonight, but I wasn't going to necessarily go back to the stuff that we just did